Hi everyone. We are going to look at a reaction in Unit 10, the amines unit, and the reaction is going to be the Gabriel synthesis. It's a new reaction. Um, After we go over the Gabriel synthesis, we're going to compare it to other ways that we've learned in the past how to make amines. So an amine is a molecule that has a nitrogen with all single bonds around it. And in this illustration, we have an amine right here. It's coming off of the protein opsin. We'll get to this biological example in future videos, but this amine reaction right here between the protein and this aldehyde is very important for sight. But let's figure out how to make the amines via Gabriel synthesis. Now, Gabriel, they're referring to Sigmund Gabriel, German chemist. So there is no relationship to me. And this synthesis was discovered in the late 1800s, but it's still pretty useful, and I know several people who still use this method to make primary amines. So before we actually get to that synthesis, what is a primary amine? Because what you want to remember is Gabriel synthesis of primary amines, one of the most common ways to make an amine. Well, a primary amine is, again, a molecule that has a nitrogen, and that nitrogen has all single bonds. And in the case of a primary amine, there's only one R group attached to the nitrogen. So this is primary. And another example is this. So even though the nitrogen is attached, in this case to a tertiary carbon, that is still considered a primary amine because that nitrogen has two hydrogens and one R group. How about a secondary amine? We replace one of those hydrogens with an R group. It doesn't matter what kind. You could draw the H like this. You don't have to draw the bond. Typically, people don't draw the bond coming off of a nitrogen. So that's a secondary amine. Another way you could show this, or another example, is maybe we could make it cyclic. Okay, whoops. And there has to be hydrogen there to make it neutral. So those are secondary amines. Tertiary, no hydrogens on the nitrogen. So this is, how can we call this? The common name of this is triethylamine. And an example of a cyclic tertiary amine could be this. And just put an R group there. Oh, I'm not going over official nomenclature for amines in this video. I might do that later in later videos, but I do want to jump right into this synthesis. There's actually one more classification. Actually, there's two more, but let me go over quaternary. Quaternary amines are pretty unique because, well, how do we get four R groups onto the nitrogen? You go to force it and make four covalent bonds, something like that. But you know that nitrogen with four bonds and no lone pairs has a formal +1 charge. All of these other nitrogens should have a lone pair, or do have a lone pair. Okay? And they're all neutral. There's a very important quaternary amine in your body, and that is called acetylcholine. And acetylcholine looks like this. You have what's called an acetyl group, and then choline starts from that oxygen to the nitrogen, and we have three more methyl groups, which makes this partial positive. Acetylcholine, one word, and it's a neurotransmitter. The neurotransmitter are important for memory and cognitive function. Memory. And These quaternary amines are unique in the sense that plus charge is really hard to get rid of. How do you break a carbon-nitrogen bond? It's not like you could do, for instance, a deprotonation, right? If we had, for instance, this amine under acidic conditions, amines are basic, and that would have two hydrogens and a plus charge. But we could easily make it neutral by adding base. It's not so easy to break a carbon-nitrogen bond to get back down to 3 bonds. So these are really strong, positively charged molecules that I consider it's called a point charge. That charge is localized right on that nitrogen. Okay? And there are consequences for that in terms of the receptor, right, for acetylcholine. How is it going to recognize a full plus charge, etc. Okay. We'll go over acid-base chemistry, or at least review it in the sense of amines, maybe in a different video. But I do want to get onto our reaction for the video, reaction 10A. It is our first reaction. You know, this unit is a little bit kind of topsy-turvy. I'm not talking about nomenclature first, and I'm not even talking about maybe simpler ways to make amines. I'm going right into the Gabriel synthesis. Okay. It uses an exotic reagent called Potassium Thalamid. You want to start first, though, with an alkyl halide. Let's give us this alkyl halide here, Br. Okay. Let me also write Gabriel synthesis of, just to hammer the point, we're going to make primary amines. The first reagent is either you're going to name it literally on an exam, potassium thalamide, Phthalamide, thalamide, or you could draw it. For my class, I would like them to know how to draw thalamide, potassium thalamide. It is a ionic compound, so that N is very nucleophilic. Nucleophilic? Yep, it acts as a good nucleophile. Okay, 2 lone pairs, negative charge. The second reagent, or second reaction, I should say, is hydrazine. Remember hydrazine? Hydrazine is used in the Wolff-Kishner reduction. Okay, and yeah, I'll leave it at that. Okay, pretty exotic reagents for the purpose of doing this. NH2. Again, this is one of the more popular ways to make a primary amine. We'll see, or we'll review the methods that you've known before. Okay, but maybe I should let me go over the mechanism for the Gabriel synthesis. It's pretty straightforward, actually, at least the first half. And we have thalamid coming in to knock out this halide. And we get a fairly large complex because we're adding this thalamid to that carbon. How do I want to draw this? Actually, let me draw the thalamid part first. I know I'm going a little bit fast. You could always pause the video. I think we have it 5 carbons, right? And what is next? Now we got to use hydrazine to sort of break up this ring. Let me see how many steps it takes. If it takes too many steps, then I'm just going to forego it. but we do have a C double bond oxygen. And what's going to happen is, actually, let me put also the bromine that got kicked out. Okay. What's going to happen is we're going to attack one of the C's of the C double bond oxygen, and we're going to make, if you recall, a tetrahedral intermediate. And the tetrahedral intermediate would look like this. Yes, this is going to be kind of lengthy. And we have a plus charge right here. Okay. Huh. Okay, so what is going to happen? We're going to try to break this bond, right? That nitrogen has to stay with this carbon because that's our amine. That's our amine portion of the final product. So, we got to make this the leaving group. So we're going to do a couple proton transfers. Let me see if I want to actually do this for us. A couple ways that we can do this. Why don't I cheat a little bit? We're going to take this lone pair right here, okay, and we're going to do an intramolecular proton transfer. Okay. I wouldn't actually ask for the mechanism of the Gabriel synthesis on an exam. The reason why I'm doing this is I want you to see what the other side products are in this reaction. And also, it gives us a little bit of more practice with acyl chemistry at the carbon-oxygen double bond. Okay, we protonated this. We have still this alkyl group, and that's plus. Okay. Now this is neutral, NH and H2. Okay, it's a little bit crowded, but now we're set up to kick out this group or break this bond. Okay. We have that. What is the result of those two mechanism arrows? The result is we have, okay, good, we have that carbon-oxygen double bond. Oh, we have this now attached, NH2. Okay. We have this attached on the bottom. Oh, and here we go. We have NH, and then our organic or our alkyl group that we're interested in. Okay, I'm not going to do the rest of the mechanism formally, but what you can imagine is that, oops, not that one, but this one right here. That lone pair is going to come in and attack this carbon right there. And eventually you're going to protonate this nitrogen and then also kick that out. So what I can do here is give us a couple of arrows. Okay. And the side product that I was interested in showing you is what happens to the thalamid. What happens to the thalamid is that it ends up looking like this. N, right? That came from the hydrazine, and we still have our carbonyls. H. So this molecule here came in and sort of hooked up with these two carbons of the carbon-oxygen double bonds and kicked out, right? Kicked out finally this amine. Product. Okay. All right, not a big deal. I just wanted, again, to show you how you could possibly get this molecule or how you could take off, right, this group here. that did the substitution. Ultimately, if you want to do this in the synthesis, get to the alkyl halide and then do your Gabriel synthesis. Let me go over other ways that we've learned how to make amides. Amines. Just remember this is for primary amines. Okay. Other ways are going to be important because what happens if you don't start with the right number of carbons? Okay. So for instance, we had this problem here. We did this on the previous page, and you know to use Gabriel synthesis. And realize again that this is a primary amine. Okay. Now, what happens though if you have an alkyl halide, the same alkyl halide? And now you want to make this amine. Yeah. If you remember your carboxylic acid derivatives chapter or unit, you would know that this came from most likely a nitrile. We add an extra carbon, right? So we have plus 1 carbon, and it's still a primary amine. We're going to go through the reduction of a nitrile. Use reduction of nitrile. How would that look like? Simply you take sodium cyanide, NaCN, and do a substitution. That's a good nucleophile. You know that it's the triple bond N. So I draw the triple bond N to remind myself, well, what do I need to do to get to the single bond to nitrogen? Well, I have to reduce. I'm reducing the triple bond down to a single bond. And that, if you recall, is lithium aluminum hydride. Okay. Again, this is a past reaction. This might be good as a final exam review. Okay. And again, we have a primary amine with 1 extra carbon. All right, we'll zoom out. How do we do these primary amine syntheses? We have one here using the Gabriel, and we have one here using reduction of nitrile. I haven't shown you how to make a secondary amine. Let me show you that. Again, this is review, but maybe the synthesis is a little more difficult than just drawing the products of a reaction. So how to make secondary or tertiary amines. Okay. Let's see. Let's give ourselves an amine, secondary amine. How about that one? Okay. Well, again, from our carboxylic acid derivative unit, let's do a retrosynthesis. Again, this arrow means comes from, and it came from possibly the reduction of an amide. This is an amide, right? And this is an amine. All right. So that's going backwards, or comes from. So going in the forward direction towards our target. Do you remember the reagent? It's still lithium aluminum hydride. Okay. So if we get to the amide, we could get to amine. So this is a secondary amine, correct? Well, so what could be a possible synthesis? A possible synthesis could be, well, how about this? Let's combine a couple things. Let's say we have to start with bromoethane. Okay. Hopefully you could tell that that's going to be, ooh la la, that's going to be these two carbons. Okay. Well, I want to make this the amine, and we'll use Gabriel synthesis. We can't use the reduction of a nitrile because we would accidentally add a third carbon, right? And I really do want to make this amine on the right to eventually make the amide. So I don't typically like writing out or spelling out the reagents. I would rather draw the structure. Potassium Thalamid and H2N and H2. Oh, by the way, if you look up this reaction, the Gabriel synthesis, on online, you could also use for number 2, or 2 could be just NaOH. Well, what you would do is you would hydrolyze under basic conditions, hydrolyze the bond here and the bond here to have a diacid on the left-hand side, and that would release the primary amine. Okay. So if you use NaOH, you would have a diacid instead. Dicarboxylic acid, I should say. Anyway, here's our primary amine. Okay. You could react this with an acid chloride to get the amide, and then you do the reduction. If you're not given an acid chloride, do you remember how to make the acid chloride? Maybe from an alcohol. This alcohol right here. Okay. Typically for a synthesis, you're not going to get a starting material that's that fancy. You're typically given a starting material like an alkane, alkyl halide, or an alcohol, but probably not an acid chloride or even a carboxylic acid. Well, we're going to convert this into the acid chloride, but first we have to oxidize it. Potassium dichromate, H2SO4 is a recipe for the Jones reagent or Jones oxidation. And SOCl2 to get this. Now, if you have a convergent synthesis, the grader should recognize or should understand what you mean when you do something like this. You bring those two starting materials together, and you do get, I think you get the right amide, I hope, that we want. Okay, this is our target. Okay, and then yes, do your reduction. 1 LiAlH4, 2 H2O, and this was the weird reduction where just get rid of the C double bond oxygen. Okay. All right. So now what have we accomplished? We've accomplished now how to make a secondary and tertiary amine. To make the tertiary amine, obviously you'd have a tertiary amide, right? And how would that occur? You would have to make the secondary amine to attack your what do you call it? Your acid chloride. Okay. Imagine if this was a secondary amine, then you would have another R group right here. So in that case, you wouldn't start out with the Gabriel synthesis because you really need a secondary amine, not a primary amine. Anyway, again, you're making, in this case, a secondary amine, or you could make a tertiary amine from the tertiary amide. If we zoom out, those are three ways to make amines: the Gabriel, reduction of nitriles, and the reduction of amides here at the bottom. Now, did I have anything else to talk about? Oh, you know what I forgot? There's actually one last classification, and that is, I'm going to go back to the first page, and that is if you have no R groups. Okay? You know this already. You have NH3. That's neither primary, secondary, tertiary, or quaternary. That just has its name and its ammonia. Okay. Is there anything I want to talk about ammonia? Oh, yeah. Let's use ammonia in the synthesis of an amine, and then I'll stop the video. There's one other way to make a primary amine. It's kind of a weird way to make it, but you could make it through the amide. So if you have, for instance, let's say this carboxylic acid. Okay. If we go ahead and convert it to the acid chloride, some of you may know where I'm going with this, and then I react it with ammonia, and I get this primary amide, and then you could go ahead and do your reduction. We don't add any carbons. Okay, we started out with 3 carbons for the carboxylic acid, and we do end up with 3 carbons for now the primary amine. Is anything more preferred than the other? Well, it just depends on the starting material that you get. Okay, if you had an alkyl halide, I would rather do the Gabriel synthesis. Here we have a carboxylic acid. You might as well go through the amide and then reduce the amide to the amine. Okay. Okay, I think that's it. Actually, we're going to learn, I think, one more way to make amines in a future video, and then we're going to do several reactions using amines. Very interesting reactions, including the reaction that I discussed here, where you have an amine, in this case a primary amine, connecting with an aldehyde to make this type of bond. Okay, so you have that to look forward to, but I'm glad that we were able to get started with this unit with Gabriel synthesis.